Okay, this is a recorded lecture for section 4.4 in the Bowerman book for MGT 5030. We're in chapter 4 here on probability. This is the cover photo of the Bowerman book, 5th edition. And for the purposes of this recorded lecture, this video, I expect that getting up through 4.4, you should be able to handle fairly well. It's fairly straightforward concepts as we get in there. But in the conditional probability and independence, I wanted to cover something and give you a work tool that works a little bit better than trying to handle a bunch of these different matrices that we use. So within conditional probability, we talk about contingency tables, or we talk about crosstab tables, or cross-tabulated tables or matrices. Okay, and the idea here is that I think the first thing to do, we'll take an example, make sure that you've worked through this section 4.4, but I want to show you a little bit of a better way to look at this, or maybe a faster, more complete way to look at this, so you don't lose situational awareness about where you are in a problem. Because once you start reading a problem, the word problem doesn't spell everything out to you. And if you draw your matrix and you draw your Venn diagram to begin with, you'll have all the waypoints that you need to get through the problem. Okay, so I expect that you can understand the gist of the problem by reading the section ahead of time, doing the Learn Smart for the section. We have a cable company that has television, internet service, phone, other services. We have a cross-tab matrix here that only shows two of the different kinds of products that the customers can have. They can have television and they will have internet. We want to look at the interrelationship here. This is still, we're still just taking a look at the raw data that comes out of the cable company here. Okay, when they create this crosstab, they have some numbers. Now, we don't always have all these numbers, but what we can do from this simple start that they give us on here, where they do give us all the numbers, we can identify the different pieces of information that all go together. Okay, so I have some of this reproduced over in Microsoft Excel, and you'll notice I have a bunch of different matrices shown because we have to calculate different things. And so I just took a screenshot of the book that we just had there, and this is the crosstab data that we have. Things to note here, I wish that they actually drew this a little bit better. I think they were a little bit lazy, but you have to help yourself out wherever you can. So I draw in some lines and say, hey, okay, so here's our four quadrants. We have two variables. Each of them have two different states, equally complementary, that a customer either has television or they don't have television. They either have internet service or they don't have internet service. And we're looking at the quadrants, the four combinations of two variables, each with two different states that we can get. And just to get familiarized with our matrix here, we have the number of customers that have television and internet is 6.5 million people. The number of customers that have internet service but no TV is 3.3. If we add them up, 6.5, 3.3, we get 9.8. What does that tell us? Okay, so we're adding up this column. It says all of the internet service customers add up to 9.8. Okay, if we go to the first row, now I'm going to use the first column and the first row because they are the most significant to what we want to talk about here. If we work across columns here, we walk across the row that we have here, we're going to add up 6.5 million customers that have TV and internet services, plus the 5.9 million customers of television that didn't buy internet. They didn't buy the combo package there. Okay, so they have this is the number that have both the TV and the internet. This is the number that have just the TV, no internet. And when we add those up, we get a total of 12.4 million people. Okay. Now, if we add all four of these numbers up, they're all exclusive. Okay. And that should add up to 27.4 million. Okay. So all these four add up to 27.4. The number of customers that have internet service plus the number of customers that do not have internet service, you add those up, that's going to be 27.4. And if we add up the number of customers that have TV service and the number of customers that do not have TV service, that all adds up to 27.4. Those are three checks that you want to make so that your data has integrity, it's complete, and there's no mistakes in there. Okay, so now I just took this table as is, if you kind of draw some lines in here, like such, like this, all right, I just completed out some of these lines here, then you'll have the matrix that I have up here, and now they're live data in Excel. You can see as I click that, I've just retyped in the 4 quadrants that we have. I just typed in the numbers, then I did a sum on the column, sum on the column, sum on the row, sum of the row, and then I did an add of the column data, and I checked that with the add of the row data here, and they're equal. Okay, so the 27.4 million. Now, you do have to read the chapter and the section that we have here to understand how these problems are set up, but these are completely cover the sample set that we're interested in. There's no gaps in here. That's why if you add the numbers up, it comes up to the total number of customers that have TV and or internet service. Okay, it's 27.4. Okay, so what we do with this is we immediately can do some simple calculations and say, what's the probability of any one of these quadrants and even the sum rows? What's the probability along these different dimensions, okay, if you will, right? So there's 24% chance that a customer will have both TV and internet. There's 6.5 divided by 27.4. So all we did was for each of these quadrants, we divided it by the total number of customers. Okay, so this is the frequency, and then we divide that by the total population of 27.4, and we get the corresponding probabilities. And now, across the rows, we can add up the probabilities. So the probability that a customer will have TV is 45% chance. 1 minus 45% chance is 55%. See how these are complementary here. So this row here represents the customers that do not have TV. This is the number of customers that, percentage of customers that have TV, okay? And those that do and those that don't, when you add them together, they have to equal to 1. And likewise, when we calculate the probability that a customer has internet, so remember B is the internet service, okay? Right. So the probability that a customer has internet service is 0.36 or 36%. Okay, 0.36. The probability that they don't have internet is 64. We know that because 1 minus 0.36 gives us 0.64. Right. So if you add those two together, you're going to get 1. All right. So that's just a check. All right. So I can move this off to the side or actually delete it. Let's just delete it. All right. Okay, so there we have the bare statistics. Okay, now if you remember the section that we're in, it has to do with the probability of certain things happening. Okay, so already what we've done is we've calculated 3 of the 5 items that we're after. Okay, so let's go to the Venn diagram. We always want to draw the Venn diagram. We could have done this first. I would have recommended to do it first to make sure you get a total picture of it between the tabulated data up above. Here's your Venn diagram. We'll draw A like such. Okay, so remember A is equal to those that have TV. They subscribe to the TV. And that number, the total number would be 12.4 million. Okay, so we have a number, but we also have the probability that it's 20, actually it's 45%. Okay, so 45% of the customers, can you think of this as 12.4 million customers or 45% of the customers? Then we have B. B is a number of customers that have internet, so we'll draw that also. Now B is a little bit less. Okay, the number of people that have internet is 36% compared to 45%. So this number, if you're gonna, or this circle, this graphical representation of B is equal to the number of people with internet, or the percentage of people that have internet, like that, will be a little bit less than A. Okay, you can actually see it. It's something on the order of, let's see, we've got, it's on the order of 9.8 versus 12.4 million customers, something like that. That comes out to something on the order of 4 to 5. Okay. although we don't really need that, but it is to keep in mind situational awareness about your problem. So if you run into a problem, you might recognize it. Okay, so we've done two things. We have tabulated data now. We have a Venn diagram here. I'm going to go get myself a different color pen. All right, let's go with blue. Let's get a blue up here. I'd like to have a clear, something that's really blue. That's blue. All right, very good. Now I have a blue pen. All right, so let's identify in the Venn diagram some of the things that are going on up in the top here. And what we can say is that here's the probability that the customer has internet. Okay, so this circle here, B, is the number of people that have internet. And we have that number right here is 36%. And this is the probability that they have TV. Okay, and that's this circle here. Okay, right. So what is this other thing that I colored in yellow up here? Okay, so that thing up there, if you look at it, that is going to be the probability. So we have a probability of A, give it a check mark. Probability of B, we know what that is. Probability of that it's both customers with both TV and internet. Okay, that's what this box is up here. Okay, so that's P and B. Okay, it's intersect means that it has to belong to both groups there. So sometimes it's marked as a little and symbol, something like that, or the word and that I just used to use that. Now, in conditional probability, the thing that we want, what we're trying to do is we're trying to, once we reduce the set from the population down to some characteristic that we know. So for instance, suppose we know that the customer has internet service, what's the probability that they also have TV? Or vice versa, given that they have TV, what's the probability that they have internet? And these are the 5 parameters, basically, of our set that we're interested in, okay? This problem comes up frequently enough. There's actually currently a lot of push in communications and logic and thinking and debate right now with the state of fake news and everything that people get a little bit more familiar with logic. Okay, so we're dealing with some logic here about how things work, and we'll get into Bayes' theorem regarding this. And if we understand that, we're getting double duty here because we'll use it in business, but also, as I said, as a matter of sort of societal communications right now, is lacking in pure logic. All right, so you will see that pop up quite a bit. Okay, so now we've got three of the 5 things that we need to know. So what is the conditional probability, given that we have internet service, what's the probability that it is also a TV customer? Okay, and what we can look at is here's the intersection right here. Okay, and then we also have the probability of B here. So we can look at what the probability of A is this circle with respect to this greater outer box here. That's the greater population. And likewise, the probability of B is its circle with relation to the greater area within the box there. Those are 2 things we have. But now what we're saying is we're restricting it to say looking. Let me grab another color here. I think I have to add another color. Do I have a green up there? Let's go with light green. Okay, so we'll do light green. I'll pick that. Okay. So given B, now that we know B, within B, we just reduced the entire set to B. What's the probability of A? And A is going to be this intersect here, okay? Right. So when we look at the frequency, what we're going to say is it would be, remember we said this box up here is going to be the intersect of where A and B overlap, okay? This is where you get both TV and internet customers right there. So the proportion that we're going to have is going to be 6.5, and this comes right from the book here, over the total B. This is the probability of B. Remember, I have it written down here. Okay, so probability of B is 9.8. So there's 6.5 million customers compared to 9.8. Okay, and that's probability of A given B. That's what we get there. So in order to do that, I have the next matrix here. Okay, so we have one replication of the original data here to figure out the core probabilities of any one part of any one of these quadrants or any one of the summed columns or rows here. But now we have to have another matrix, and what I'm going to calculate here, here's the intercept, right? So the intercept, what I'm trying to find out now is not just the intercept, but I'm trying to find out A given B. Okay, and to do that, we're going to take B3, which I just explained is B3, here's column B, and 3 is the intersect divided by the total of B, right? Probability of A given B. So it's going to be it's going to be 6.5 over 9.8. That's what that number is. It's going to come out to be 0.66. So what we just calculated there is now our P A given B. That's that one, okay? But now switching colors, let me grab something I don't have. We'll try red again. Okay, so now we got that, right? So now we have to get probability of B given A. So again, it's going to be here's the row with A in there, okay? So given that of these 12.4 million people that have TV, how many people also have B? That's the intersection here. So we now have to do a 6.5 instead of, remember we did over 9.8, now we're going to do 6.5 over 12.4, okay? Because that's the probability of A, don't forget what that is. So that's what this next calculation over here is going to be, okay? So if we go up there and I click on this cell, you're going to see now we're going to take B3 and we're going to divide it by D3, just to make sure I have my numbers right, okay? And we ended up coming up with so up here we have the probability of B given A. Okay, so now we have all 5 of these things figured out. Okay, so instead of having all these different matrices with different numbers, why don't we create one matrix at the very beginning of this, now that we're familiar with these kinds of problems, and we always need these 5 different pieces of information uh, to calculate one or another one of these missing. We don't always have all the data. This is the whole point is if we need to calculate some piece of information here, why don't we create the table from the beginning? And that's what I'm going to give you here is a way to create that with the 5 pieces of critical information. If you dive into these problems the same way, you draw your matrix the way that I'm about to show you. If you draw your Venn diagram, you have your original data here, okay? You can put it all into one matrix, okay? And it's just an issue of style to be able to combine it together, okay? So if you remember, when we did the probability of B, okay, we kind of looked down the table at the probability of B down here, and we look across the table for the probability of A, because the probability of A ends up over here, the probability of B down here, right? But we also have to look at what the value is against the total population. Okay, so notice those 3 directions. Well, what I created here were 3 boxes. I'm just going to order them so you can see what I'm talking about. You can see there's a little square around those, okay? So we can figure out the probability of B in this box. What's this? The probability of A intercept B here and the probability of A here. We're just going to use these boxes now. Notice A, I've spread these out a little bit. They're not as tight in these boxes. I've actually formatted some cells here a little bit differently, but you can use this. You can draw this on a piece of paper. Okay, so now when you draw this kind of thing, you have A naught. Okay, so in Excel, I always put the little naught afterwards. I don't have that fancy overscore type thing we've got there. And then we have B and B naught. And up here, we're going to have 4 numbers. We're going to have the raw number of the count, and we're going to have the probability of B here, the probability of A here, and the probability of A intercept B. And they're in the directions that they relate, that we can relate to in here, okay? All right, so let's go ahead. Now that I did all that, I'm going to delete it. I'm going to pause here for a second, delete some of the overwriting that I did here. So I've done a little bit of formatting here, and I've got 5 cells in this eventual matrix that we've got that represent the 5 pieces of information that we need here. I've marked them in yellow. And what we're going to do is I'm going to show you how they work. The reason why I have, here's the sheer number of customers that have both TV and internet here, but I want to calculate the probabilities that we had, remember? Okay, so let's actually do this one. This is the probability of A. Okay, so the first one here, probability of A, because we're adding up along the row where A is the TV customers that we have, right? Okay, so the probability is going to be equal to total number of A by the entire population. Okay, there we have our 45. If we go back to our earlier number, there's that 45. Okay, now let's do the probability of B. Okay, so that is going to be equal to the total number of customers that have internet access divided by total number of customers at all, right? And there's our 35. Okay, it says 30.36, or it's been rounded up from 0.357. Okay, so that's probability of A, probability of B. Okay, now the probability of A intersect B is going to be the number of customers that have both divided by the total number of customers. It's in this direction, this diagonal direction, so I'm going to put it down in this diagonal box from the original number here. So that's going to be equal to 6.5 divided by 27.4. Okay, so that's about 24% there. Okay, so that's going to be, if you remember, that is going to be probability of A intersect with B. That's down here, this little blue squiggle area. Okay, and finally, right, what we want to get up here is going to be the probability of A intercept, A given B. Okay, so here we have the total number of B. We need the total number of A intercept with B by the total number of B. Okay, that's going to be equal to, given that we know they have internet service, here's how many people have TV service divided by the total number that have internet. Remember? There we go. Okay. And then this is going to be probability of B given A, okay? Because we're saying if we know that they have TV service, of the 12.4 million, how many of them will have internet service also? So this is going to be equal to intersect divided by the total number of A. Okay. And there's our 5 pieces of information. Look how fast that was. As you get familiar with these problems and you use this matrix over and over again, and you have the Venn diagram over here to refer to when you need it, you given all that, all you really need is this a type of box like this with the 5 pieces of information in there to go and solve for which one might be missing. Okay, so that's the idea here. Is in this problem we've given all the information. So in the world of descriptive analytics, descriptive statistics, we were able to describe data here. Okay, we took what we were given, we were able to describe certain behaviors here. I added a couple more notations in this matrix that we have here. But one thing you can do is you can set up one of these matrices. You can actually add a comment in here. If you're using Excel, go into insert comment, and you can just say that that's the probability of A given B. And you'll get that little red triangle there. Okay, so this would be commented in as, that's the probability of A. I don't have an upside down U. What do I use for U? I usually just like that. Okay. That's A intersect B. This is the probability. So what I have in here is an annotated matrix where we ended up. You might want to add these comments in here, insert comments. Although I did put it here on the column header, this is the probability of A. That should read better as this. Correct that. Okay, so I'm putting comments in here. What we have marked here is probability of B given A, probability of A given B, and this is the probability of A intersect B. There's probability of, that should be probability of B. That's a comment to correct it. And just, all right, so if you put your own comments in like this, you can reuse the matrix, but just going through one of the problems this way, in fact, if you want to reproduce the problem here right in the chapter, try to get where I got to here with this, this is a good way to replicate these problems over and over and over again. As you hit these, you can figure out which parts of the data that you actually are given. Okay, sometimes you might be given the percentages. The next problem in the chapter has to do with percentage of women that have management positions that are also salespeople. Okay, and they only give you the percentages here, so you have to go back there and fill it out. The extension of the first part of the video, where we talk about conditional probability. What's conditional probability? That says that we have a greater population, and we pick a sample, and we identify that one of the two different parameters. Okay, so the two parameters that we're talking about would be is a customer a subscriber to TV, which is A, and are they a subscriber to internet, which is B? And we can ask such questions as, okay, so how many people have both? Okay, such things. Okay. And the idea behind conditional is, okay, if we do pick a sample and we immediately identify the fact that they have internet access, what is the probability that they also have TV access? Okay. And if you look at this, keep in mind that there's a ratio. What is the percent of the total population that has TV subscription? And now we've reduced the greater set. We said, oh, now we know it's B. It's a smaller subset of the grander number of all customers. When within that, what's the probability? We have to look at this intersection. That intersection is going to give us that area over this total area. It's going to give us that probability A given B. Okay, that's what we just did. Right? So now let's look at it graphically. Let's understand the next part to identify here is here's the conditional probability, all right? And is the ratio to the entire population of customers that have TV, that is A, okay, is the proportion of those that have TV to the bigger population the same as once we know they have internet, is the ratio of the population of A to those that have internet, is that equal to the same ratio to the population? That's independence. If these things are equal, that means we have a homogeneous population. Okay, it means that doesn't matter whether we know that they already have internet because the population of those that have internet is exactly the same as the ratio to the larger population. If that changes, okay, so just think about that. So the independence, the item of independence here says that the ratio shouldn't change. It should be homogeneous, okay? So if we have all these people here, okay, and let's say green is internet and red is TV, okay? We have a lot more people that have TV, for instance. Okay? We have all this, okay? What we say is, okay, everybody that's red go to the left, everybody that's green go to the right, okay? There's colors here. Okay, so here's our total population. Okay, so everybody that's red move to the left, everybody that's green move to the right. And what ends up happening is when they get themselves all sorted out, they occupy something like this. Let's say that 75% of the total population has TV. Okay. Now here's the tricky part. I have to draw this kind of carefully. All right. Let's go. I think we need green here. I said green to the right. Okay. Now what we're saying is now that the green moved to the right, this is the green. Okay. This is going to come out okay. Okay. So we count up. You see, we have more red than we had green. I said that. I drew a lot more red dots than I had green. Okay. And when we started counting things up and looking at frequency, we said 75% of the population has TV, and the green, far fewer of them, or some fewer of them, have internet. Okay, and this is what you're going to look at now. Instead of using circles, I'm using boxes. No big difference here. Okay, it's just easier to show you the spatial relationships here. Okay, so if you look, the red is 75% of the blue, and then the intercept. Boy, I guess I need yellow. See what happens here. Okay, and I color in this intercept. Remember from the previous page here, the ratio of the intercept. Now that we know that we're talking B, that ratio has to equal the larger homogeneous ratio. Is it homogeneous all the way through, or are there more people with TV clustered within those that have internet? Suddenly, once we have internet users, does that say that we have a higher population suddenly, a higher relative population of TV people subscribers, or do we have a smaller group? Is it less dense in here than the greater population? That's what we're talking about, how to configure or discuss. Okay, so that's how we talk about independence. Okay, all right. Let me say that another way, in a shorter way. Okay, another way to say it is: do we have an advantage once we know that somebody has internet? Is there any reason that the population within the internet users, that the TV users, is higher or lower? That would mean that it's not homogeneous with the entire population. That for some reason there's a higher density or a lower density in the given, in the fact that we know that they have internet. That is the total concept behind independence. Now, how do we express that in ways that, or in the manner that we've already been talking about things? Remember the 5 items that we calculated so far? Now that we have the 5 basics of all this, right? That just goes to say, is the density, the frequency in the greater population, right? The probability that you have A in the greater population, is that the same once we go to a subset, once we go to B, once we have another subset in there, what's the probability of picking a customer with TV subscription out of the group that has internet? They have to be equal. If these are equal, that means the ratio of A, the intercept of A's in the B, that means that there's no change in density when you go from the larger population to some subset defined by, for instance, customers that have the internet, that the density doesn't change, that the same proportion is there, right? So in other words, it'd say if our greater population had 75% of them had TV, it doesn't make a difference that we know that they have internet, that within that subgroup, it's still 75%. Okay? But you can see the reason why we're interested in independence is sometimes we'll start noticing something that, well, the idea of marketing here is that maybe we find out that if somebody already has internet, if we know that they have internet, maybe 80% of them have TV. Okay, that means that there's a higher density once we know that there's from the subset there's a higher density of people that have it. It's more likely, in other words, this is things we use every day. Go back to that. Is if we know that they have internet, it's more likely that they have internet that they have TV.